Hello everyone. Today's video we will be talking about the remainder of section 4.2, part of which we covered last time. If you guys recall, section 4.2 talked about the first derivative test and concavity and inflection points and stuff like that. You can see on the screen that I already have some stuff written, and that's because my audio didn't record for the first 10 minutes of me doing this. So I'm just going to go over what I already wrote instead of rewriting it. So this is just a reminder from last time. We defined concave up as when our first derivative, or our slope, is increasing. And I told you guys you can remember it as up like a cup. So this kind of looks like a cup. That's a concave up section. And then concave down was when our derivative is decreasing, or our slopes are decreasing, and that was down like a frown, looks like a frown. Okay, so the newest portion of this section is a test for concavity, so that's what I have written right here. I would say this is cheat sheet information. I just think it's useful, especially since you guys are allowed your notes on exams now. So our test for concavity say, first of all, if our second derivative is greater than 0 on an interval a to b, open interval a to b, then our actual function is concave up on a to b. Okay, so if we look at our little drawing up here where it's concave up, our first derivative is telling us that the slope is increasing. Right, so our first derivative is getting larger. We start at a negative slope, flatten out, and then become a positive slope. And what the second derivative is telling us, remember, a derivative is a rate of change, so the second derivative is saying the change of the slope, right? And if my slope is getting more positive, aka if my derivative is increasing, that change in slope needs to be positive. Okay, so if we have a second derivative that's positive, then we say the actual function is concave up on a to b. Similarly, if our second derivative is negative, that is, the change in slope is negative, our slopes are decreasing, which means we have f as concave down on a to b. Finally, if our second derivative changes from positive to negative, or negative to positive, at some point x equals c within our interval, then we know that f has an inflection point at c. So last time we kind of talked about inflection points. For example, an inflection point would be right here. We change from concave up at the bottom to concave down at the top. Okay? So this point right here would be an inflection point c. Okay, so the final thing that I wrote before this video canceled itself was this theorem, which is called the second derivative test for local extrema. You can also just call it the second derivative test. I don't think anyone actually says the full thing. This is certainly a cheat sheet item. It's a named theorem. I want you guys to know this. Will certainly be on your next exam. So remember, for theorems, we always have conditions that we have to meet before we can use the theorem. And in this case, we need to suppose that f double prime, or the second derivative of f, is continuous on an interval a, b. So that's our first assumption. Basically, all that's saying is you have to be able to take the derivative, the second derivative, everywhere on our function. If you can't take the second derivative, i.e. if it's not continuous, it's not defined at some point, then this theorem doesn't work, just because we need to be able to use the second derivative to use this theorem, so if it doesn't exist, it's basically pointless. And then we need this interval to contain some point x equals c, and we need the first derivative at c to equal 0. If you guys remember from last time, if the first derivative at c equals 0, then that was called a critical point. Okay? So then, this theorem basically has 3 parts. So the first part is if f double prime, or the second derivative, at c, so at that critical point, is greater than 0, then f has a local minimum at c. So basically, what's happening here is it's saying f double prime is greater than 0, so that means f is concave up at c, which we know looks like this, right? And c, in order for our first derivative to be equal to 0, at c would have to be this bottom point down here, and that's a local minimum. Okay, so hopefully that makes some kind of intuitive sense to you guys. The second part is very similar. It states that if f double prime of c is less than 0, f has a local maximum at c. So again, when our second derivative is negative, f is concave down at c, so it's going to look something like this. Remember, down like a frown. We know our slope is 0 because we said that c is a critical point, or f prime of c is equal to 0, so it must be this guy up here, which is a local maximum. Alright? And then the third point says, if f double prime of c is equal to 0, then the test is inconclusive. That basically just means, like, this test doesn't work, you're going to have to use a different method. Okay? Okay. Basically, that's because in order for f double prime to be equal to 0, we would have to have f prime be equal to some constant, and that is just a straight line, right? That would mean f prime of c is a straight line somewhere, and so that could be a local minimum, a local maximum, or both, depending on what your graph looks like. Yeah, so you just have to use a different test. We're gonna do, let's do one example of this, and then we'll call it a day. Okay, so, here, this whole thing is the second derivative test, and it's important that you guys know that. Wow, that was not successful. Okay. Alright, so for our example, let f of x be equal to 3x to the 4th minus 4x to the 3rd minus 6x squared plus 12x plus 1, and consider the interval -2 to 2, and I want us to find the local extrema, extrema on this interval. Obviously using the second derivative test because that's what we just did. Alrighty, so step 1 is obviously to take the derivative. Here, let me write it in red like I have been doing. Take the first derivative, because if we look back up at our theorem, we know the first step is that f prime at c needs to be 0, so we need to find all those critical points where f is 0. And just to comment on the fact that f double prime is continuous, We know that it's continuous because it's a polynomial, and polynomials are differentiable everywhere for all derivatives. Okay, so we're taking our first derivative. We have f prime of x is equal to 12x cubed minus 12x squared minus 12x plus 12. And we need to find all those critical points, which we know is where the first derivative is equal to 0. So find critical points. So we're going to set this guy, our first derivative, 12x cubed minus 12x squared minus 12x plus 12 equals 0, and solve for x. We can divide everything by 12 and get x cubed minus x squared minus x plus 1 equaling 0. At this point, if I were you guys, I would just use a computer algebra system like Symbolab to solve or to factor this. And we get x plus 1 times x minus 1 squared, which is equal to 0. We did this example before, actually, so this factoring should be somewhat familiar. And that gives us x equals -1 and x equals +1. Okay? So for step 3, we need to take the second derivative If we take the second derivative, it's just the derivative of the first derivative. So we'll get 36x squared minus 24x minus 12. And step 4 is to plug critical points into the second derivative. So for x equals -1, we have f double prime of -1 is equal to 36 times -1 squared minus 24 times -1 minus 12, which is 36 plus 24 minus 12, which gives us 48. Okay, and we know that 48 is greater than 0, so according to our second derivative test, if our second derivative is greater than 0, f has a local minimum at c, and c in this case is -1. So in an answer, f has a local minimum at x equals -1, and we would find that minimum by plugging -1 into f of x. So f of x was 3x to the 4th minus 4x to the 3rd minus 6x squared plus 12x plus 1. So we have 3 times -1 to the 4th minus 4 times -1 to the 3rd minus 6 times -1 squared plus 12 times -1 plus 1, which is 3 plus 4 minus 6 minus 12 plus 1. Let's see if I can do quick math. That's 8 minus 18, so -10. Okay, so our local minimum is at x equals -10, and the actual value of the function there is, at x equals -1, and the actual value of the function there is -10. All right, we have one more critical point to plug in. At x equals +1, we have f double prime of 1 is 36 times 1 squared minus 24 times 1 minus 12, which gives us 36 minus 24 minus 12, which is 0. So the test is inconclusive. And at this point, we would go back to our first derivative test. So if you guys remember from our first derivative test, we need to show that our function is changing from either positive to negative or negative to positive. So we're going to look at our number line at x equals 1. And we're going to calculate f prime at certain points on either side of it. So we know that f prime of x equals 1, or f prime of 1 is 0. And let's take a point over here on the left, say x equals 0. F prime of 0 is equal to, if we go back to f prime, we had this for f prime. So at 0 we would have 12 times 0 minus 12 times 0 minus 12 times 0 plus 12. So that's 12. So we know our first derivative is positive to the left of x equals 1. Then we'll take a number to the right of x equals 1, let's say x equals 2. And we get f prime of 2 is equal to 12 times 2 to the third minus 12 times 2 squared minus 12 times 2 plus 12. And that is 12 times 8 minus, oh god, can I do this math in my head? 96 minus 48 minus 24 plus 12, which is greater than 0. So we also have that the first derivative is positive over here. So we aren't seeing a change in derivative, which just means that x equals 1 is not a maximum or a minimum. Okay, so f has no other local extrema. Okay, so that would be how you use the second derivative test. We'll certainly be using that in the future. We have to do a lot of problems with maxes and mins later, but that just introduces the test to you guys. Again, the most important thing is that you guys have this theorem, and the steps are pretty helpful too. Step 1, take the first derivative. Step 2, find critical points. Step 3, take the second derivative. Step 4, plug the critical points into the second derivative. Okay? Alrighty, see you guys later.